それでは時間になりましたので、東大する7月の談話会を始めさせていただきます。本日の座長を三竹先生にお願いしております。よろしくお願いします。
Okay, so let me start. Okay, so it's a great pleasure to introduce Professor Juan Manfredi from Pittsburgh University. Okay, let me introduce about him in Japanese. マンフレディ先生、関連に従いまして、日本語でご説明いたします。マンフレディ先生は、セントルイス・ワシントン大学において、1986年に学位を取得され、1989年から現在までですので、35年以上の間、ピッツバーグ大学において長く勤められております。ご存知の方も多いとは思いますが、ご専門は楕円型、放物型変微分方程式で、特にp ラプラス方程式や、あるスケールをとって p を無限大にしたときに現れる、いわゆる無限大ラプラス方程式のご研究において、国際的にリードされる研究者の一人です。で実際p ラプラス方程式の解の正則性滑らかさに関するご研究結果は大変重要なものでありまして、この分野に多大なインパクトを与えられております。でまた個人的にはマンフレディ先生の論文で学んだのが例えばp ラプラス方程式の粘性解等長関数の同値性といった基礎結果であったり、インフィニティラプラス方程式の固有値問題に関するご研究など、またあと特に最近ではハイゼンベルグ群といったサブリーマニアン多様体上での解析でも精力的にご研究をされております。またご研究以外にも、ピッツバーグ大学において、全学のバイスプロボストと呼ばれるポジションなんですけども、英語で少し日本の方に馴染みない言葉なんですけども、副学長という全学のそういった立場に長く務められておりまして、大学におけるその行政的にも非常に重要なポストを務められてまいりました。はい。で、okay, so now it's good time to start. And okay, once again, it's a great honor to introduce him. And the title of his talk is Asymptotic Mean Value Expansion for Solution to General Elliptic and Parabolic Equation. Please.
Thank you very much, Professor Mitaki, for your kind introduction. Though I didn't understand what you said, I imagine it was good, so thank you. It is a great pleasure for me to be here, visiting the University of Tokyo and having such an esteemed audience to listen to what I have to say about mean value expansions, which, as you will see as the talk develops, is really another name for viscosity solutions, or at least in most cases. Okay, so let me give an overview of what I hope to say. So I will first talk about very well-known theorems about mean value formulas for solutions of linear equations, recording some of the basic results at some classical results that we all know and study in our courses. Then I will talk about some heuristic and possible applications of what I'm going to say to explain how things work. And then I will have two main examples that I will discuss in some detail. The first example will be about the Monge-Ampère equation, and I will go through certain stages, defining things. I'm providing some details, but not complete proofs. And then I will talk to the Heisenberg group and the p-Laplacian, which is the operator that I love in the Heisenberg group. I will study that in that particular setup. Of course, this includes the case of Euclidean spaces. Okay, so the unifying theme is that these mean value properties are sort of meta-equivalent to viscosity solutions. So it's interesting to find them, especially in the case of nonlinear equations. So let me start with some very, very classical results. And the first thing is the Gauss-Keve theorem. At least that's what we call it in the United States. So you have a function that is smooth in some domain, and then you have the Laplacian. The function is harmonic, so it's a solution of the Laplacian. If and only if it satisfies the mean value property, you have the center of the ball, is the mean value of the function on the ball, whenever this makes sense, whenever the ball is defined in omega. So this is a characterization that we all learn possibly as a problem in case of when we take our first PDE course. Notice that condition 2 makes sense only for continuous functions or for integrable functions. You can write that down. And no further regularity is required for 2. While for 1 in principle, you need the function to be C2. Now consider a weak form of condition 2, in which you have the mean value property plus an error term, which is the little o of epsilon squared. Now we assume that this is true, so clearly 2 implies 2 prime because there is no error term, but it's also not difficult to see that 2 prime implies 2 whenever you have smooth functions, because you can do a Taylor expansion and it's just, the coefficient of epsilon squared is precisely the Laplacian. So if the coefficient of epsilon squared is not 0, then the Laplacian will be equal to 0. Okay, so this is all very classical. So now I have a theorem or an observation. Suppose you have now a continuous function. Then I claim that the following are equivalent. Condition 2, which is the one we had before, which is the mean value property that we know implies the function is harmonic, and condition 2 prime, which is the same thing with the little o. Okay? And little o, of course, means that what it's supposed to mean, always. So you can see that you have to think a little bit to go from 2 prime to 2. Because to go from 2 to be harmonic, well, we can differentiate here and we can get the U is smooth, but to proceed. But here, to go from 2 prime to 2 or 2 prime to harmonic, you have the error term. This is a point-wise definition, so it's not so easy to differentiate. So of course, the explanation is that 2 prime implies that U is harmonic in the viscosity sense, and therefore harmonic, and therefore we get 2. Okay? So this is an observation that says that the asymptotic mean value property contains the same information as the regular mean value property. You can get the same properties for U from 2 prime down for 2. So we can, replace Laplacian U equals 0 by Laplacian U equal to some function of x. And then the Laplacian U is equal to f, if and only if, when you compute the coefficient there of the O epsilon square, you get f of x. So this will be equal to the Laplacian. So if the function is smooth, then this is in the classical sense. And if it's not smooth, it is true in the viscosity sense that I will later define. But probably in this audience, I don't need to. Okay? So already a Polish mathematician, Kosakiewicz, used this approach in 1933 to define second-order differential operator on continuous functions. So this will be more general than the Laplacian. So this is an old idea that has been around. And I think now with viscosity solution, we can close many loops. Okay? So this is, what the message of this slide is that the information contained in the asymptotic mean value property is the same as in the regular mean value property. Okay? If there are any questions at any time, please stop me. So let's recall two classical theorems of Bldg and Parabolic. So an upper semi-continuous function is subharmonic, which could mean that the Laplacian is positive in the viscosity sense, if and only if, well, the difference that we computed before is not negative. Okay? And when you change the sign, you get the same thing for subharmonic functions. So this, of course, doesn't look very new to us here today, but in 1916 or 1925, no Sobolev spaces, so people thought of good ways to prove that the sum of two subharmonic functions are subharmonic, especially when they're not smooth. There was no easy way. This now allows you to prove that if U and B are subharmonic, so is the sum, because this is a linear relation. Okay, so that was interesting at that time, is because when it wasn't clear what the regularity you need and there was no distribution of Sobolev spaces, this gives a way to prove some properties of subharmonic functions. I think Bldg did the spherical means, so when you average only on the sphere, so the average is on the sphere and you take the surface area, and Parabolic did everything, solid averages. And, but the square is the same power for both. It's just that the average changed, but the square remains the same power. Well, so that's just a classical application of these ideas. Now, we also have discrete mean value properties. So what does it mean? So a function is harmonic, say in the viscosity sense, or of course in the case of the Laplace operator, it could be on any sense, because they're all equivalent. If and only if you now take a point x and consider, x plus epsilon e1 minus epsilon e1, x plus epsilon e2, x minus epsilon e2, and then there are more dimensions, more of this, and you average out the value over all of this. So it's 1/2 for each of the x. And you allow for a small error, which is O of epsilon squared. Then it is true that the function is harmonic, if and only if this is true for every point, whenever epsilon is small enough. Okay? So there is a discrete asymptotic mean value property that also is useful to characterize harmonic functions. And sorry. We can then, every time you have one of these properties, you can consider the relevant property without the error. And we can define discrete harmonic functions at the scale epsilon to be a function defined on the closure of the domain that is equal to some boundary values which are defined on the complement of the domain. And whenever it makes sense, you have the corresponding inequality. And if the ball of radius x plus epsilon goes outside of omega, you just use g there. So we have this. This is now an equation, right? Which is this is a problem. You have some discrete Laplacian here, and then you have the boundary values, and then it's a good exercise to prove that under suitable conditions, maybe omega and g ellipses, though this is far from optimal, given any epsilon is small enough, there is a unique solution to this problem. And moreover, the solution converges to U uniformly in omega, where U is the solution of the Dirichlet problem. So this is a well-known fact, which I don't know if I can give you a reference, but you can prove this on any PDE course. So here we see a phenomenon that we'll see later, is that asymptotic mean value properties provide semi-discrete approximations. So these approximations are semi-discrete because we still have continuity in x is in Rn, but the epsilon parameter, when you compute the averages, is a discrete set. Okay? So we call them semi-discrete, maybe for lack of a better name. And finally, you can also consider Brownian motion. Brownian motion is starting, say, at a point x, and then you watch out when you get out of the ball. So there is the stopping time tau boundary, which is the first time we go out of the ball. And then, of course, you are at the boundary of the ball. And then a classical theory of Kakutani is that a function of u is harmonic if and only if for every ball u is the mean value computed with respect to the Brownian motion measure when the Brownian motion starts at x. So this was so somehow almost in every possible way we can write the mean value that is sort of a reasonable rotational invariant and so on. We get back to harmonic functions in many different ways. Okay? So we have seen the regular Gauss-Keve theorem, we have seen the asymptotic Gauss-Keve theorem, discrete mean values, maybe mean values with respect to Brownian motion. So there are all of these things. So what are more results of this type? Well, I call these linear results. So these will be results that are for linear equations. If you replace the Laplace equation by a second order elliptic equation with constant coefficients of this type, then everything is true, but you have to replace the balls by ellipsoids. Everything is more or less true. You can put second order elliptic and parabolic equations with the smooth coefficients, but then of course then the formulas, only the asymptotic formulas work, because on a manifold you don't have the rigidity you need for the full Gauss-Keve theorem. And in fact, you can put subelliptic equations in the Heisenberg group and Riemannian manifolds, and all the local theory extends pretty well. So the linear theory you can consider in great generality. So what I'm going to do during the rest of the talk is, what are the analog results for nonlinear equations? Are there mean value properties that are useful for nonlinear equations? And I will, so I will present two examples in some detail, Monge-Ampère and k-Hessian equations in Rn, and the p-Laplace equation in the Heisenberg group and in R3 in this case. So that will be, but the gist of the talk is to find out, are there nonlinear versions of these theorems? So before I go into some details, let me give a heuristic remarks in the nonlinear case. So there is some sort of meta-equivalence that this will become theorems if you give specific details, but of course, in each case you have to prove the details. For a real function, we have a meta-equivalence among some mean value property in an appropriate asymptotic sense. So if the question is nonlinear, you have to do it only asymptotically. You solve a possibly nonlinear PDE in the viscosity sense. You can be approximated by solutions to a dynamic programming principle associated to a semi-discrete stochastic game or control problem. And we'll see what that means. This is the equivalent to the discrete case for the Laplacian. Or finally, U is the value function of a stochastic game or control problem. This is the theory of nonlinear stochastic differential equations. I will not say anything about the 4-point other than it's there, and you can look at it. But the first three are what attracted my interest. So one of the advantages of probability, at least advantages from my point of view, is that in probability the domain doesn't matter. You can define a probability in very abstract spaces, and you only take functions, a real value function. So probability frees you from the geometry. So this approach, makes sense in Euclidean space, Riemannian manifold, sub-Riemannian manifolds, graph, metric meshes, and so on. So in principle, you can define many equations in metric spaces. They may or may not make sense. The definition may or may not agree with the one other people use. But it's sort of formally you can write many things. The ones that I will, when I know things work, are the p-Laplacian, the infinity Laplacian, fractional p-Laplacian, the mean curvature equation, their parabolic versions, and some special systems that are almost diagonal. So this is, from that point of view, is good because you can extend many results in principle, at least consider them in different geometries, different ambient spaces. But there is a basic limitation, is that we use only equations, not systems, because we rely a lot on comparison principles and maximum principles, which for general systems are not true. So that's the limitation of this theory. And as far as I know, there is no progress on some sort of viscosity solution for systems, but there might be in the future. So this is what I try to show now, and I think my first example will be the Monge-Ampère equation. First application, sorry. So we got the heuristic now, the application. So though of course I'm not an applied mathematician, but I have seen other people use these ideas. So one can write nonlinear partial differential equation in graphs and metric measure spaces. And Adam Overman and his group, they have used this. Machine learning, semi-supervised learning, the group of Jeff Calder in Minnesota has been using the p-Laplacian for this. I will say more in a few minutes. Development of novel computational algorithms, Félix del Teso in Madrid and other people. So when you have a fractional p-Laplacian, this at least will give you some numerical method, which may not be the best, but in some cases is the only one we know. And this is used a lot in image processing, and the group of El Moataz at Caen in France use this all the time. So in the majority of these applications, there is a common theme, is that the Laplacian, so this is all has to do with the Laplacian in a graph, the Laplacian in a discrete set. And as you know, for the Dirichlet problem, points that have capacity 0 cannot be seen with the Laplacian. So in a discrete case, when you use the Laplacian, you run the risk of missing a lot of information. But if you use the p-Laplacian for p bigger, large enough, let's say, then a point has positive capacity. So you never miss it. So the Dirichlet problem for the infinity Laplacian, for example, is always well posed, no matter how bad the boundary is, because points have capacity 0. So in all of this, for example, in semi-supervised learning, they use p bigger than the space dimension, and then they get algorithms that converge. For p equal 2, you essentially never know. You may lose some information because points are not, a single point of information is not seen when p is equal to 2. So that's more or less what this is done. So I will not say more about this other than I am always happy with, I'm quoted by one of these people, so saying that this has to do with something that I did before. Okay, so I guess I have to define viscosity solutions, even though it's not neither in this audience, but we have equations of simple type of equations, f, gradient second derivative. F is proper, which means decreasing in the second derivative variable. And the examples that I consider are the Laplacian and the infinity Laplacian and the p-Laplacian. These are the three basic examples we'll see. And Monge-Ampère, but so upper semi-continuous function is a subsolution. If every time you have a function that touches from below, or u minus phi as a local maximum, that we have here, then when you plug the test function inside f, you have the appropriate sign. For these equations, you can delete the points where the gradient is not 0, and that does not change the equation, but you have to prove it. I put it there, but so you see that's the test function touching u. So, for example, at this point, there is no test function, so the equation is satisfied because you cannot find a test function to contradict. And here there will be many, many test functions, and you can see there's always plenty of test functions for any given u. So that's the definition of viscosity solution, which we know we transfer the PDE from the function u to the function phi. So let me now start with the Monge-Ampère equation. So as you know, this is just the Hessian of u equal f, and we want f to be positive, omega a convex domain. So, which is the best of all possible worlds here. In terms of eigenvalues, that simply means that the product of the eigenvalues of the Hessian equals f. And we specifically want convex solutions, so all the eigenvalues are positive. For example, in the plane, these two functions are solutions to the equation determinant of the Hessian equal to 1, but we only want this one because this is the one that is convex, so we're making a choice here. So I'm going to talk about some mean value properties that satisfy this equation. When is the function phi for technical reasons that will become clear in a minute, which is from R to R, at 0 goes to infinity, but when you multiply by epsilon, it goes to 0. When epsilon goes to infinity, sorry, that's a misprint, infinity. For example, 1 over the square root of epsilon, that works. So here is a first mean value property for solutions of this Monge-Ampère equation. Remember, U is convex, C2 omega is convex. We're in the best of all possible worlds. So U is equal to the infimum, and you have all these averages on ellipsoids, because x plus ay when y is in the ball of center at 0 radius epsilon is an ellipsoid. And we want the determinant of A to be equal to 1. But you don't want the ellipsoid to degenerate, so A is bounded about by phi epsilon identity. Remember, when epsilon goes to 0, phi is going to infinity, so this restriction is being relaxed. So we have the mean value property, all possible, the infimum over all possible ellipsoids, minus epsilon squared, a coefficient n over 2n plus 2, f, which is that one, to the 1 over n, plus little o epsilon squared. Again, we see that wherever multiplies epsilon squared, modulus a constant is really the operator that you are considering. Okay? So this is the equation, and I call this the local case for following reasons. So the metrics are symmetric and positive definite. That's so for every A with determinant equal 1, the integral on the ball center at 0 radius epsilon of Ux plus Ay is the integral on the ellipsoid, the average on the ellipsoid. So as phi epsilon goes to infinity, the restriction disappears on the limit. But still, this formula is local in the following sense, that when epsilon is going to 0, the distance from the ellipsoid to the point x, you can compute, triangle inequality, still goes to 0. So for a small epsilon, these ellipsoids are included in omega. So the formula is still local. The ellipsoids don't go far away, because eventually they will be in omega, so it will make sense to consider the mean value formula. So this is well defined whenever x is in omega for small epsilons. Okay, so there is also a non-local version which requires to use more properties of the Monge-Ampère equation, in which you simply replace this condition that A is bounded by phi epsilon identity by asking that you just want to be able to compute the integral. So this ellipsoid is contained in omega. So now you have the following thing, but instead of having that A is bounded above by some epsilon, some function that goes to infinity with epsilon, you just want this to be in omega. Now this, of course, is a little bit more complicated, because if omega, is Rn, for example, then you can make this ellipsoid very long or very thin. And you still have the determinant 1, but it could be the averages over a very, very, span set. So this requires some more properties of the Monge-Ampère equation, so the proof of this non-local convection equality is quite more difficult than the other one, but and it uses more Monge-Ampère machinery. But we're glad to know that is true. Okay? So you can have that. So now we go to the viscosity case. Okay? The viscosity case, we have now a continuous function and a convex function u, and the following are equivalent. U is a viscosity subsolution to the equation, that is, the determinant is bigger than fx. U satisfies this 1/2 of the asymptotic mean value property, and the one on top is by using the local version. The one on the bottom is the non-local version. But we want this inequality to be satisfied in the viscosity sense, which means not for u, but actually for test function that will touch u from above or below. So we're asking this, what do you have there? You replace u by phi. So that means, so this inequality holds in the viscosity sense means doesn't hold for U itself, it holds for all of the test functions. So we are transferring the information again to the test function as we do in the definition of viscosity solution. So that, is a characterization, both of these, and that gives, that again shows that viscosity solution and mean value and asymptotic mean value theorem are the same in this case for the Monge-Ampère equation. So what is the discrete version for the Monge-Ampère equation? So you want to have now a discrete version, and then here you take again averages over the same lattice that we had before, but now you have to consider all possible orthonormal bases, and each axis is weighted with the number alpha, with the square root of alpha, that the product is equal to 1. So that's to say that the determinant of the ellipsoid is equal to 1. Right? And you want this number to eventually go to infinity, but controlled by phi. So you can then prove that when you take the infimum over all possible orthonormal bases over all possible chases of weights, that is the same as the infimum over all discrete ellipsoids of the corresponding average. That is equal to whatever multiplies epsilon square, which is the operator, plus little of epsilon square. So this is the discrete version now applied to Monge-Ampère. So let me say a few things about the proof of the mean value formula for Monge-Ampère. What are the ingredients of the proof? And I only going to emphasize on the key, or one of the key difficulties. So these are regular mean value formulas. The mean value of a constant is a constant. The mean value of a linear function is 0 because of the symmetry of the ball. And you take a matrix M, you get epsilon squared improved trace of M. So we know this. And then we need to relate the determinant with these operators. So the determinant is the infimum over all traces. So armed with this information, you take a point and do the Taylor expansion and integrate on the ball, right? So the integral of u0 is u0, the linear term disappear, and here u turns out to get this. So at least, and we assume that the determinant is positive, that the Hessian is positive definite. Then of course you take infimum in both sides. You put the infimum here over all a's, determinant 1, and you put the infimum on this side, you get the infimum there, and that's it. And that's the formula that we had before. But of course, we have to be careful because we have an O of epsilon square, which is certainly not uniform in A, and here we have the infimum and the O there. So there is the analytical difficulties to justify this. How can you justify this? So we need to justify the exchange between the infimum and the little o. And then, of course, when you write down what you need that this mapping M goes to Fm, which is the infimum of the trace, that mapping is continuous on the cone of, on the correct domain, which is this particular cone of all m's, which are positive definite, with this trace is bigger than minus infinity. So, in other words, you can do this whenever f is a continuous function of the second derivative. Then you're allowed to exchange, and then you get the asymptotic mean value property. Okay, so that's really as you can see, formally this is quite simple, except you justify this in the local case. In the non-local case, you have to do more things, but follow the same scheme. Okay. So I talk about parabolic cases in the title. So let me give a couple of examples. So you get the solution of this parabolic Monge-Ampère when you have du dt equal Monge-Ampère plus some source step f, and u is convex in the special variable, so this is always positive. Well, this is true in the viscosity sense, even only if you have this expansion, which is the same as before, but we also average in time. Time scale is differently, but it's the same thing. And the proof is the same. You just, do the Taylor theorem including time and carry out all the terms. So that's an example. In general, for elliptic to parabolic, in most cases, it's not very difficult. Now, while we were working on this, we saw there is another parabolic Monge-Ampère that people use, which is minus the UDT times the determinant of the Hessian equal fxt. So we wonder whether we can write the same formula for this, and you can by going to the m+1 times m+1 case, and then you can more or less figure out that the same thing works. So I don't know, some people in geometry use this equation. So we just wanted to know if we could do it here. Right? So I think this is my last Monge-Ampère talk. Oh, no, sorry, I had the discrete version, okay, which is very important. So I'm going to briefly describe a one-player game or a control problem or an optimization problem that will have as value functions solutions of the Monge-Ampère. So we start in some domain omega. We have some payoff function. So maybe here, do I have a picture there? I will put here. We have some domain omega. The payoff function is defined on the boundary here. This is the payoff function, which is when you get out that plays a role. And we have some running cost function f defined here. This is the running cost. Which is defined in omega. They are non-negative, and we fix some number, positive epsilon, and we took an initial number, an initial point, x0, and then there is one player who is playing, and the player has to decide where to move, where to go to the next value, x1. And in order to do that, he chooses an orthonormal basis, V1, Vn, and n real numbers, which are the eigenvalues of the ellipsoid, the semi-x of the ellipsoid. So this will be the information of the ellipsoid, and then the token is moved to x0 plus minus epsilon square root alpha vi, with equal probabilities 1 over 2n. So there are, of course, n x's, so each of these is 2 options, so 2n. So with equal probability, you move to the next one there, then you move to the next one there, x2, and eventually you will be out. And then you stop. Of course, every time you move, you pay the running cost. So every time you move, the running cost is f of x0 to the 1 over n. It has to be a scale properly, so we let epsilon go to 0, it's 1/2 epsilon squared. Okay? So that's the game. Now, repeat the process to go from x1 to x0, get a sequence, and the game starts when the token leaves omega, and the first time is tau. You have to think about this probability fact. The game ends almost surely because the random walk on 3 dimensions will leave any domain. And at the end, the player gets paid a certain amount of money, which is g of x tau. But every time he moves, he has to pay something. So his total balance, the payoff minus what you have to pay. It's all of this. So for every run of the game, this is the amount of money you have at the end of the run of the game. Now, strategy is a choice or orthonormal basis and eigenvalues for every partial history of the game. There is a formal way to do this that is sort of boring, but the point is that every strategy determines the probability on the set of all games. So you play this game many, many, many times, the average will be your expected outcome. This is how much you have. So let me just repeat. So you play the game many, many, many times, and then you average, and this is your expected outcome. So this is the value function. Okay, so here is exactly the same picture that I have here, but this will go away in a minute, and this one will remain. So Now suppose that the player wants to minimize payment. If he wants to minimize payment, he will choose a strategy that will give you the minimum amount to pay. So we define U epsilon as the infimum over all possible strategies of this expected value. Then this function satisfies the following dynamic programming principle. U epsilon is infimum over all orthonormal basis over all eigenvalues of the average that we had before for Monge-Ampère minus epsilon squared f to the 1 over n. This is exactly, there is no little error here. Satisfies this exactly. And then U epsilon is equal to G for x not in omega. So this is a version of a discrete Monge-Ampère operator, if you like. And the first thing you have to consider is while you have this, do you have existence? Do you have uniqueness? And it turns out that there is a theorem of Chin Liu and Adam Sikora. They were both at Pittsburgh at the same time working on this, and they prove existence and uniqueness. And it turns out that this is really much easier than when you have integrals, because you don't have to worry about anything being measurable here. Everything here is done with functions defined pointwise. By monotonicity, you can show existence by running a fixed point argument. The comparison principle follows easily. So there is uniqueness. So these discrete dynamic programming principles, from the point of view of analysis, are much simpler because you don't have to prove that things are measurable, which sometimes in the theory of continuous games could be quite difficult and take a lot of effort. So now that we have U epsilon, of course, the expected result is that when epsilon goes to 0, this decreases to the solution of this Monge-Ampère problem, where you have f, the running cost, is here, and the boundary values. Okay? And we wrote out the details with Blanc, Charro, and Rossi a couple of years ago. Okay? And so this is the mean value gives you the semi-discrete way to approximate, and then you can write then you can prove the convergence. Okay? So this is sort of the things that we want to do for other equations, to go from to go from some semi-discrete principle to get convergence to the continuous problem. Now here I am omitting some details, which of course you have to work out, is that the convergence in the interior, that follows from general viscosity, formalism. But at the boundary, you have to be quite more careful, and in this case we have to use knowledge. We know things about the behavior of Monge-Ampère at the boundary that we need to use this to prove the convergence. So other equations that this can be done, in particular, we want to consider the k-Hessian. So in the case of the k-Hessian, or more general operators, instead of taking all possible symmetric positive definite matrices, we just take a set of that. So this is some class A, this is F subset, and then you define the corresponding cone, which is the sort of matrices, symmetric matrices that Fm is bigger than minus infinity, and we already know that this is going to be critical. We made the hypothesis that F is continuous in this particular cone. And you define admissible solutions for which F is finite for every x of omega, and we approximate the unbounded set by bounded set that we did before, phi epsilon I. So this is a generalization, but the same proof works because the key continuity is there. So now you consider as Fk the k-Hessian operator, which is sigma k is the k symmetric function of all the eigenvalues, and is defined on the cone of functions whose eigenvalues are positive for j1 to k. They were exactly the same expansion as before. But now, of course, the cone is different, so you are the infimum is over the smaller set of matrices, but there you get the Hessian operator here. Okay? And the proof is the same as before, is that we need some formulas that I'm sure are well known to the experts, but but we couldn't find them, so explicitly proven, so we just proved them too. But this is linear algebra. Huh? So you see, this is flexible. The k-Hessian equations are also included. You can also have the product of two eigenvalues, and this will also work. And you can have more other functions of eigenvalues, but and this will work. Okay, so that's sort of the first example I described in detail. Now the next example is about the Heisenberg group, which I will give you a 5 minutes description of the Heisenberg group. But you know, it's like R3 with a different geometry. So in R3 you have 2 points. You multiply this is plus, so this is like Euclidean addition, but there is a new term there. This twisting term makes, this is a group operation. The inverse of an element is just minus, but it's non-commutative. It's non-commutative. Right? And it turns out that there is a gauge, which is like taking xp yp to the 4th power, zp squared, the 4th root. So it's like absolute value xp yp, and then a square root of zp. And this gauge has the fantastic triangle inequality, which is true, but not totally trivial. That's why you need 16. You put some other number, then you get a constant. And there is a left invariant metric. The distance between 2 points is the gauge of P inverse Q. And the key of this theory is that the dilations are anisotropic. So you have lambda x, lambda y, lambda square z. So the dilation there is different. But the dilations are group isomorphisms, and the gauge of the dilated by lambda is lambda times the gauge. So this behaves very well from the point of view of dilation. So the Heisenberg group is like R3, but it has some non-isotropic dilations. So it turns out that the hard measure of the group is R3, is the Lebesgue measure. We go in R3. And when you take the ball of, which is all points where Hessian is smaller than R, the ball is actually constant R to the 4. So this ball some epsilon square. So the ball is something like this, and the volume will be epsilon to the 4th. So as a metric space, the dimension, the Hausdorff dimension of HDK is 4. So the topological dimension is 3, but the metric space dimension is 4. Then every group has a Lie algebra. You find the generators, and these are the left invariant vector field. So this will define the operator with constant coefficients in the group. The only non-trivial commuting relation is just that x3 is x1 commutation x2. The horizontal gradient of a function is just the first 2 layers, the first 2 vector fields, x1, x2. That is really the key, the equivalent of the gradient, but now instead of having 3 components, it has 2. And the symmetrized second horizontal Hessian is a 2 by 2 matrix, which of all the second derivatives. But now because the x1, x2 do not commute, you need to symmetrize. So you put x1, x2, sectors 1 over 2. That's the way it is. Huh? And then the so-called cone Laplacian, or subelliptic Laplacian, is this operator, the trace of the matrix, which is this thing. So let me write this in Euclidean coordinates. So you write Euclidean coordinates, you get du dx2, du dy2, but du dz2 is multiplied by something that will vanish on the z-axis. So this operator is not elliptic with Euclidean eyes, because on the z-axis it will, it will fail the ellipticity condition. However, it is a good operator. It is hypoelliptic in the sense that you have a smooth solution when you have a smooth data, and you have very good estimates. And this was first proved for this exact equation by Kolmogorov in 1934. We simply wrote down the fundamental solution, which you can write with all these. It's a 2-page paper. And then Hormander proved it for general vector fields, a very substantial result. So, but this is something that you want to understand this with you have to get out of the Euclidean point of view. You have to think subelliptic. Okay. So what are the relevant mean value operators here? Okay. So look at this mean value operator. You have a function v. Yeah? So it's a mean value over a two-dimensional ball. This is the set of all A, B in R2. It's the ball of radius epsilon. And this is v. And then there's a point P times AB0 dAdV. So this is called horizontal mean value because we are always looking at this horizontal product. Okay? You could do other mean values. You could take the mean value over the three-dimensional ball. That also can be studied. You could do many mean values, but this one, I claim, is the one that gives you the horizontal Gauss-Keve theorem, which is, as before, that if you have a function that is smooth, then the mean value is equal to Vp plus something that multiplies epsilon squared, which is, of course, the Laplacian, plus little o epsilon squared. So in particular, you have the mean value property, then this has to be 0. And moreover, you can prove that if this is equal to 0, you have the mean value property. You can get rid of this. And so this is the horizontal Keve theorem with this special horizontal mean value operator. And then you can discretize by, consider a domain, and you go a little bit outside as we did before, and you consider all functions defined on omega time plus the strip, has certain given boundary values, and this operator says, T of V says that if you are inside omega, you get the mean value. If you're outside omega, you take the boundary value F. And then you can iterate this operator, and we can show that there is a unique function, such that it's a fixed point of this operator. And it's bounded above and below by the boundary data. So, by the way, functions for which you have this equality are called two-harmonious for a fixed epsilon. So, some time ago with my colleagues Levica and Ricciotti, we proved that when epsilon goes to 0, you get exactly what you expect, which is the solution that there is a problem. And so again here, the convergence inside follows from general viscosity machinery, which, by the way, can be adapted very well to the Heisenberg group. There is there is a theorem of sums, the same thing with this in this setup. So we have to follow a strategy of Barles and Souganidis, which define the half relaxed limits. So U upper bar, U lower bar, and by construction, U upper bar is upper semi-continuous, U lower bar is lower semi-continuous. And then U upper bar is a viscosity subsolution, and U lower bar is a viscosity subsolution. So we need an estimate on the boundary that you need to prove, which is not totally trivial, but right now assume that the super solution at the boundary is bounded by F, and the sub-solution above by F, the super solution below by F. Then when you have this, then of course U lower bar is always smaller than U upper bar by definition, and U upper bar is smaller than U by the comparison principle, because you have the right comparison of the boundary. Then you get that everything is equal, and then you have uniform convergence in what you need. Okay? So the key point here is the boundary estimate, which happens all the time in this Barles-Souganidis theorem, is that of course, in their paper, they're very clear. You need to estimate, you need to find out what happens at the boundary. So here, we have some boundary estimate that I'll just put here, where you have to prove that U epsilon is going to F with the proper way. And the point is that you need to get an estimate which is valid for all epsilon. So all this valid for all epsilon is smaller than epsilon 0. So that requires some work. But I will just tell you only the key ingredients. So we need to use that, the harmonic functions are the same as two harmonic functions. that there is a comparison principle, and we have a fundamental solution, which is Q inverse P. This is the Korani norm to the Q minus 2. Q is equal to 4. And that fundamental solution can be used to build barriers on rings, and this is necessary to set up then a sort of a de Giorgi style iteration to get the estimate. Right? So again, this is where you get your hands dirty, because this is one of these iterations that takes a few pages. Okay? So, but then we have recovered the theorem, you know, in space. It works also on the Heisenberg group. So now for the last few minutes, the p-Laplacian. So the subelliptic p-Laplacian in the Heisenberg group is just the Euler equation of minimizing the pth power of the gradient, and then you have the notion of weak solution, and you also have viscosity solution, and they are all the same. You have solutions by mean value properties, and they're all the same, and I'll say a couple of examples, but so we are in the same situation to start with as in the Euclidean case. And so for example, what you get in the Heisenberg group is that a function u is p-harmonic if and only if you have this special average. So this average has two parts. Then a Laplacian average with the constant beta, so this is the standard average. But here you have the so-called Tug-of-War average. It's a nonlinear average, but it's the one corresponding to p infinity. So this is an interpolation between p infinity and p equal to, and that's how you get p. Okay? And in the Heisenberg group, these numbers alpha and beta are a little bit more complicated than in the case of the Euclidean space, but you can compute them enough. So you have exactly the same theorem that p-harmonic functions have an asymptotic mean value property. A piece that we get is from the Laplacian, and another piece for the infinity Laplacian. And I cannot resist but mention a theorem of Arroyo and Llorente, and they prove that in the plane, asymptotic p-harmonic functions have a classical expansion. So not in the sense of viscosity, not touching with test function, a classical expansion. So this is a regularity theorem in the plane, and this is the way. This is not true for p infinity. You need some Laplacian here. An interesting problem that is whether this is true in dimension 3 or not. Probably false, but nobody has any counterexample. Okay, so this is an aside, but I have to say, because in this case you have actual classical expansions, but you have to be in the plane, and you have to use a lot of stuff that only occur in the plane. So we're getting to the end. So now we need to define the Tug-of-War again for the p-Laplacian. Okay? So we now have two players instead of one, and they flip a coin, and whoever wins moves. Okay, moves to, you know, at most a distance of epsilon. Okay, and then with some other probability they move at random. So there is probability alpha, Tug-of-War, probability beta at random. There is a payoff function, and when you get to the boundary, player 2 pays player 1 the amount f at the boundary. Japanese gens. Smart player will steer, you know, if player 1 has to pay player 2, if I'm player 1, I'm going to go to the maximum value of f. But player 2 wants to go to the minimum value of f. Huh? So this is the rule of the game. You are at xn. If probability alpha, you play Tug-of-War. So alpha over 2, player 1 chooses whatever point he wants in the ball of radius epsilon. This is the Korani ball. Player 2 chooses whatever point he wants in the ball of radius epsilon. And with probability beta, we just do a random placement. So the extreme, so if alpha equals 0 and beta equals 1, this is the case of random walk. But if alpha is equal to 1 and beta is equal to 0, this is Tug-of-War, which of course is first introduced by Perez, Schramm, Sheffield, and Wilson in 2008, maybe 2009 the paper appeared. Huh? So Now, each player has to adopt a strategy, decide what to move. These strategies are called sigma 1 and sigma 2. Given a pair of strategies, you build a probability on the set of all possible games, like we did before. And then you have to show that the game ends. And this is true because beta is positive, so there is some Brownian motion that is getting away to the boundary. And then you define the value function for the player. So if I'm player 1, I let player 2 to go as low as possible, and I come as high as possible. And player 2 is the opposite. And the point is that they're all the same. This is a well-defined game. The players are the same, and they satisfy a dynamic programming principle, which is the one which is like the discrete mean value, but without the error. So the U is this alpha times this nonlinear mean value, and then beta times the diffusion. So this theorem in the Euclidean case was first proved by myself, Parviera, and Ross in 2012. Then we did p bigger than 2, because in this case, p smaller than 2 is more difficult. But then other people did px bigger than 1, and then with Marta and Ricciotti, we did it p bigger than 1 in the Heisenberg group. That's sort of the one that has everything, okay? And what you get is that this discretization converges to the solution of the Dirichlet problem, okay? So that's sort of, in all these cases, the boundary estimate is the one that requires more work. But in all these cases, you know, it has been proven. So I think this is my last slide. So thank you very much. This has been a great pleasure being here.